Welcome back to ECE 441-541. If you haven't completed your passport assignment, go ahead and submit that. Your pre-quiz is due Friday. So if you finish watching the game, you actually have 24 hours to finish. I think the game's on Thursday this week, and it won't impact your parking this week. It's an out-of-town game, so you should be okay. Now, unless you're flying over, you need to maybe make sure you get parking wherever you're flying to. Homework is due a week from Friday, homework number 1, and we will get you more comfortable with the first problem after Friday's lecture. I think I'm giving you some other stuff to fill in the subsequent problems today. Today, what I would like to do is talk about, again, our best friend, the mass spring damper system, and we want to show how we can get the same quantity, the transfer function, from many different representations. We could represent that system via differential equations from the physics. The mass times acceleration plus the dash pot constant times the velocity plus k times x is equal to gamma u. That's the differential equation. We may have it in a block diagram form. We might have it in a state space representation. All of those are modeling the same system, and we want to actually show that we can obtain the transfer function from all 3 starting locations. And that's what we'll work through today. Once we have that transfer function, g of s, we can then sketch the Bode plot. We can do all sorts of things subsequent to finding that transfer function. We could hit it with a step input in MATLAB. We can hit it with a step input in the lab. We can command that mass to move a certain distance and watch as it moves to that point, and maybe we don't like its behavior. Then later in the class, we'll learn how to change that system, those system dynamics, to something more acceptable. I doubt that we will get there, but Friday we will talk about deriving or developing the equations of motion for a 3-mass system, and I think your homework first problem is a 2-mass system. So you just have to average what you've already done with Friday's lecture, and you'll be fine with the first homework problem. I think it's a 2-mass system. That's the plan. What we want to do then is develop a transfer function starting from many different starting locations or different representations based on this same mass spring damper system, and I've simply given it to you here so that you feel warm and fuzzy starting the discussion. This should start to feel very comfortable to you. We have the dash pot, we have the spring, we have a mass, we're applying a force to that, and we're moving that mass. We're accelerating that mass, we're giving it a displacement and a velocity, and we know how to model those dynamics. And let's then look at that from various representations. For example, the differential equation form for the dynamics. We could say that we now have this mass times the acceleration plus b times the velocity plus k times the position is equal to F, the force applying to that mass, but we might be applying a voltage, and then that needs to go through some gain constant, gamma, to deliver the force that we need in that location represented in our block diagram. But this you could derive from the free body diagram, and that's what I'm hoping you're comfortable with. But now, after doing that several different times, you can essentially write this equation down from memory. Now what we want to do is find the transfer function from this starting location. And how do we find a transfer function? And this could be thought of as a system of differential equations. In this case, it's a second order differential equation. How would we find a transfer function if I gave you a set of equations? Or here, I'm just giving you one big equation, which is second order. If I gave you a third order, the process would be the same. If I gave you a fourth order with a fourth derivative of x, the process would be very similar. What do we do? And maybe I will coach you by just remarking that this is a differential equation, and that's in the time domain. Hint, hint. You need to get very comfortable going back and forth between domains. The transfer function is a frequency domain concept, and that's where we want to go from the time domain. And if we're going from time domain to frequency domain, what's usually involved? Laplace transform. If we simply Laplace transform this second order differential equation, the transfer function is just going to fall out in front of us. And the transfer function is sort of nice because we don't need to worry about the initial conditions. That always made these Laplace transforms of derivatives kind of messy, is dealing with the initial conditions. In this case, we don't have to worry about it because we're really just worrying about the transfer function. So if we go into the frequency domain, and because we are specializing this to only the transfer function, we can actually neglect these initial conditions. A lot of just capital letters and periods, but I think you know what I'm saying. Initial conditions, IC, and TF transfer function. If we do that, what happens to the above? Well, let's not do that. What happens to the above time domain differential equation? What happens when we Laplace transform m second derivative of x? We just multiply by s squared, don't we? Every derivative gives us an s, a multiplication by s, and m we're assuming is constant. That's not a function of time, so m is a constant. The Laplace transform just slides right through that. Likewise for the other one, and I probably should have put the s squared in front of the m. It usually looks a little neater. So I'll put it in front of the b. SB x of s plus k x of s is equal to gamma u of s. From that, we can simply factor out the common factor or term on the left-hand side, which is the Laplace transform of the position, capital X of s, leaving us with s squared m plus sb plus k times x of s is equal to gamma u of s. The transfer function that we're interested in is this relationship between the input, u, and the output, in this case, is our position, x. And g of s, then, is the ratio of x of s, the output, whatever we decide the output is going to be. In this case, we're assuming it's the position, divided by the input, which we've agreed is u of s. And now that simply becomes gamma over ms squared plus bs plus k. Or we might want to make the denominator monic. A monic polynomial simply means the highest power's coefficient has been normalized to 1. If we divide the mass out of the denominator and shift it upstairs so that now we just have an s squared downstairs, our transfer function in another representation could be gamma over m over s squared plus b over ms plus k over m. And now we've gone from the time domain differential equation representation of this mass spring damper system directly to a transfer function, capital G of S. And we have some numerator coefficient. We don't have any finite zeros. We have two poles, and depending on the values of the spring constant, the damping coefficient, and the mass, that will impact or influence where those poles are located. That should be fairly straightforward. What about the block diagram case, where we are now going from a block diagram representation of our mass spring damper system, and from before that was some gamma over m, and here let's go ahead and just start this block diagram in the frequency domain. Here is our input u of s. That went into a summing junction, and that then was scaled by 1 over s. In the time domain, it was integrated. It was integrated again in the time domain, or scaled by 1 over s in the frequency domain, to produce the Laplace transform of our output x. And we had more terms going into that summing junction. We had a b over m that was scaling the signal from the first integrator's output. We had a minus k over m and now I've absorbed all of the minus signs into my coefficients, which allows me to simply assume that every signal going into that summing junction has a positive sign. And that should be consistent with what we have found in previous lectures, that block diagram. And you could look at that in the time domain if you wanted to. Like I said, if I gave you a gift and said, oh, here's a block diagram of a system, provide me the all-integrator block diagram. That would be pretty straightforward, I hope. You would simply erase the 1 over s in those blocks and replace it with an integral sign, and now you have the time domain block diagram, all-integrator block diagram. Now what we want to do is we want to find the transfer function between the input u and the output, the Laplace transform of our position variable, capital X of s. And one approach to doing that, we're going to simply use block diagram algebra, which really just means adding and multiplying on the block diagram or with the block diagram. And a strategy to help you work through that, sometimes it's helpful to work from the output of the summing junction. Just find equations for all of the, if you had a bunch of summing junctions, you might just start at the outputs of those summing junctions and start writing the equations associated with those summing junctions. Here, let's just label that signal as W of S to provide us with something to call it. W of S is the output of that summing junction, and that's equal to everything coming in. Coming into that, let's just sort of go counterclockwise. We have gamma over m times u of s. We have plus k over m times x of s. Oh, and just for grins, let's do another labeling here so that we don't have to do too much in the first step. Now we have, are you guys waking me up? You're not very quick, or you're just trying to be polite. Either way, I'll assume you were just trying to be polite on a Wednesday morning. Thank you. But that's now minus k over m x of s minus b over m x sub 2 of s. And that is pretty easy. We've simply written a true statement. We've maybe introduced some new variables, but it's a true statement. Now what we want to do, ideally, this equation, or this equation in the frequency domain would only have capital X's and capital U's and some coefficients and S's. And then we could simply find X over U. We don't have that because we injected or we introduced some new variables. What we need to do now is rewrite W in terms of X and rewrite X sub 2 in terms of X, and then we'll have just X's and U's with S's and coefficients. Then we can solve for X over U. That's what we want to do. Well, the first thing we can do is we can relate X sub 2 and W. Pretty easy. We can say that X sub 2, I'm going to scroll and try not to scroll it completely off. And do I really need to stick with the colors? Not really, but just for fun I will. X sub 2 I made green. And my operator was, whoops, my stylus is not responding. I guess that's what I could always blame it on, couldn't it? If I make a mistake, it was the stylus's fault. Is that okay? That statement. Is that a true statement? I think it is, which now allows us to say that if we have X sub 2 or W, we can write it in terms of the other one. X sub 2 is really just in the time domain the integral of W. So X sub 2 of t would be the integral of W of t. What about, we can do the same thing with X and X sub 2. They're related by that operator 1 over X. X of S is simply 1 over S times X sub 2 of S. But I now have X sub 2 of S in terms of W, and I want to find an equation that relates X and W. Let me replace X sub 2 with 1 over SW, and now I have 1 over S squared W of S. Which allows me to say that anywhere I had W of S in my equation before, I can replace it with S squared X. And if I do the same thing, I'll highlight for those that are paying attention online. Now I can do the same thing for that equation and relate X sub 2 to X. I can also say then that X sub 2 of S is equal to S X of S. Anywhere I have an X sub 2, I can simply replace it with S times X. And that's what I need. I now have my desired relationships between these new variables that I introduced before to just make my thinking or my analysis easier. And now I can simply replace those W's and X sub 2's with an equation or a function of X. Let me now go back to my first equation right here and substitute for W and substitute for X sub 2 with the newly found expressions in terms of X. On the left-hand side, I had W, so that now I have S squared X of S. On the right-hand side, I had a gamma over m u of s. That's okay. I simply need x's and u's. I have a minus k over mx. That's fine. I don't need to change that. And then I had a minus b over m x sub 2, but I'm going to replace that with an s x of s. Now let me simply pull all my x's onto the left and keep the u term on the right. And I now have an s squared plus b over ms plus k over m, all times x, equaling gamma over m u of s. And if I cross multiply, I now have my transfer function, g of s. I have now upstairs gamma over m, and downstairs I have s squared plus b over ms plus k over m. And again, I found the same transfer function for the mass spring damper system when I started from a different representation initially. I started with a block diagram representation. Are there questions about that process? And it can get a little bit more tedious trying to chase your tail around some of those block diagrams, but if you try to look at the outputs of the summing junctions and then write everything in terms of what you need, which is usually the input and the output, then solve for the ratio at the very last step, and you have your transfer function. Questions on that? That's the second way. Let's do the third way, which is the state space representation. Now we could have done this via Mason's gain, and that would involve paths and loops, and we could almost immediately write down that transfer function. But we can also do it with block diagram algebra, which is what we did. So we'll leave it at that for now. Let's now look at the state space. The state space, a state space representation that we had found before was x sub 1 was our position, x sub 2 was our velocity. That's now 0, 1 minus k over m minus b over m, x1 of t, x2 of t, plus 0 gamma over m u of t. This 2 by 2 matrix was our system matrix A. This 2 by 1 column was our input matrix B. And we also, in this particular case, we said our output Y was our position, which we're now calling x sub 1, when we can write that in terms of our normal output equation, which is some matrix C times the state vector plus another matrix D times the input. Creating x1 of t from this matrix product and some matrix product is pretty straightforward, I hope. You can see that you simply have to do a 1, 0 for the output matrix C, and we didn't have any input directly feeding into form our output Y, where this is now the output matrix C, and a lot of times we don't even include that additional piece, 0u, since it's just 0. But that's our direct feed-through matrix D scaled by u. And if we wanted to write that in a more compact form, we could simply say, oh, that's simply x prime of t, where now x prime of t depends on the system. And in this particular mass spring damper system, we know that that x is actually representing a tall, thin column of derivatives, but it only has two rows, an x1 and an x2 that we've now differentiated. We have an x2 or an x prime equaling a x of t plus b u of t, and y of t is equal to c x of t plus d u of t. Somebody could say, oh, you have this linear state space representation. You know it's this form, ax plus bu, y is equal to cx plus du. Somebody now just has to give you this, the matrices, the system matrices, the A matrix, the B matrix, the C matrix, and the D matrix, and now you're good to go. What do we know about the system matrix A dimensionally? It's always square, isn't it? The B matrix generically is rectangular. It could be a column, it could be a really wide matrix. Typically your output matrix is short and wide in this class because we usually only worry about one output, and we might have 3 or 4 on the exam, maybe 10 or 12 states. Just trying to keep you alert. So let's now, if I had 12 states, what's the size of A? 12 by 12. We have 144 entries in that matrix, a 12 by 12 matrix. That'll keep you busy on the first problem of the exam. So now we need to invert that 12 by 12, but it's going to involve some symbolic terms. It's going to be scaling or having in it s's, because this is now in the time domain, isn't it? That's just a set of differential equations, coupled differential equations, written in a standard form. Let's now Laplace transform that because we want the transfer function in terms of A, B, C, and D. And now if you go home, you can say, oh, I just learned my ABCs again, right? But we're using those ABCs to find the transfer function G of S. Let's now Laplace transform this. And now take note that x prime is not a scalar generically. That x is a column vector. It could be 12 rows tall. But we're simply performing that Laplace operation on each row individually. Don't have to worry that it's a vector. We just Laplace transform each row separately. Then we need to Laplace transform the right-hand side. Just for fun, let's keep track of the initial condition in this leftmost side Laplace transform. Do you remember just in general, if you Laplace transform a derivative, what that looks like? That expression, if I say Laplace transform x, or let's say Laplace transform z prime of t. What is that? What's half of it? What's the first half? S times z of s, right? You just multiply by s if you have a derivative. In this case, we remember that this is a vector, so that we now, when we're Laplace transforming that, we now have s, and now we signify that we're in the frequency domain by making that capital, but now that capital X of s is a capital X sub 1 of S and a capital X sub 2 of S, capital X sub 3 of S, depending on how many rows we have in our state vector. Capital X of S is a tall, thin column vector. But then, if we're keeping track of initial conditions, we need to subtract X of 0 minus. And that too, or that also, is a tall, thin column, and that's initial conditions. If our state vector was position, velocity, temperature, voltage, current, say we had 5 states, then this says that we know, or we need to know, what the position was at time 0 minus, what the velocity was at time 0 minus, temperature, voltage, and current. Question? So what we're doing is we are actually, if you go back to the governing definition, let's say, of the Laplace transform, we are using the fact that we are going to capture the initial condition at time 0 minus, and then we will sort of worry. That's capturing everything we want at time 0. We want to say what's happening right before 0, and that's now our initial condition. So we're just using this in the standard form, and this is now t is equal to 0 minus. That's not s. So in this case, in capital X, this has an argument of the frequency variable s, but this is now times 0 minus. So if you go back to all of your, let's say, 320 material, if you look at the Laplace transform of the derivative, it's going to be s z of s minus z of 0 minus. And that's how it just works out. And so you're now keeping track of, or you need to know, the initial condition at time 0 minus. Okay? So now what we want to do is we want to, that's the Laplace transform of the left-hand side. We can now Laplace transform the right-hand side. And this is the really difficult part. Not. We have a constant a and x of t. Laplace transforming x of t is just capital X of s. And the a is a constant. So this now becomes a, let me just go ahead and do this in 2 steps, plus b times the Laplace transform of u of t. And that's simply now a, capital X of s, plus b, u of s. In this expression, s is a scalar frequency variable. That's just a one-by-one value, s. But it's now applied to a vector. And we have that same vector on the right-hand side. We have a times capital X of s. What we want to do is combine that capital X of s with those 2 terms. Right now we really can't do that because we have a scalar s on the left and a matrix A that's n by n. So what we want to do is actually introduce a placeholder, which is an identity, so that now we can have I being the same size as A. I is an n by n matrix, the identity matrix, and X, capital X of t, or I'm sorry, capital X of s, is a vector of size n by 1. And that's why we introduce that placeholder, that identity matrix, so that we can now combine those 2 terms, this term on the left with this term on the right. We can factor out a common capital X of S. Meaning, let's take that A, X of S, to the left, where we now have Si minus A times X of S. Let's take the initial condition to the right-hand side. We have equal to X of 0 minus plus B U of S. And now we can solve for capital X of S, which is just the Laplace transform of our position. The Laplace transform of our state variable, X. If it was a scalar, if it was our position, then it would just be a scalar X of T's Laplace transform, capital X of S. If we now solve for X of S, remember, this beast on the left, this Si minus A, is potentially 12 by 12. It's a matrix. We have S, a scalar, times this identity matrix, I, and so now we have S's along this diagonal. And that now is being added, or minus A is being removed from Si. If that's now a matrix, we can't just divide by that. We have to multiply by the inverse to isolate capital X of S, which says that we now have Si minus A inverse X of 0 plus Si minus A inverse B U of S. And that's now the Laplace transform of our total state. We have an initial condition term. Whoops, and I've sort of forgotten my 0 minus. We have an initial condition term, which makes up part of our state vector. And we have the forcing term due to the input. If we inverse Laplace transform this, we would find X of t. We would find the position, velocity, temperature, voltage, and current for that particular system as a function of the initial condition and the forcing function u. What's the Laplace transform of our output equation? Our output equation is sitting over here. Are there any dynamics there? Are there any derivatives? No. This one's pretty easy to Laplace transform. This is just basically a linear equation that relates the state, the input, to the output y. And there's no derivatives, which means or allows us to simply say that the Laplace transform of y of t, or capital Y of S, well, maybe I'll just go through it like we did before. Laplace transform of y of t is equal to the Laplace transform of Cx of t plus du of t. But that simply says that we have y of s is equal to c x of s plus d u of s. And that's now our output equation. We're trying to find a relationship between our input and the output. We have the input and the output, but we have this state vector here, capital X of s, but we have an equation for it. Let's just replace that right-hand side, or replace this capital X of s with what we know it equals on the right-hand side, two equations above. We would then have y of s is equal to c times si minus a inverse x of 0 minus plus c times si minus a inverse b u of s plus, we don't want to forget that d u of s piece. And that would give us the total output in terms of initial conditions and forcing function u, if you needed it. We really didn't need all of this. I just sort of did it for fun. I included the initial condition in this derivation, but the transfer function allows us to do what with that equation? If we're interested in the transfer function, what can we ignore or not worry about? Initial conditions. So now we'll neglect the initial conditions because we really don't need them in the transfer function, and we now have y of s is equal to c times si minus a inverse b u of s plus d u of s, but that u can be factored out from those two terms, and we have c si minus a inverse b plus d u of s. And this is our transfer function, where A is potentially 12 by 12. That's a square matrix. That's n by n. B is n by m, Nevada by Michigan, let's say. And C is P by n, Pennsylvania by Nevada in dimensions. Let's see what we can, if we can get the same g of s from our equations that we know A, B, C, and D. Remember what A, B, C, and D were up here? There were our A, B, C, and D. D was going to help us. It was nothing. It's 0. So we don't need to worry so much about D in our transfer function expression. But now we have some coefficients floating around, but A is only 2 by 2. So we need to invert a 2 by 2 matrix symbolically. Let's do that. Here is, so we want to work through this g of s expression for our particular example. And our mass spring damper system has D equal to 0. No direct connection between the input U and the position X. Then we have G of S is equal to C SI minus A inverse B. G of S, now just plug in the matrices. C, that was 1, 0. Then we have S times I. What's I in our example? That's a 2 by 2. It's an identity matrix. It's 1, 0, 0, 1. Minus A, 0, 1 minus B over, whoops. That's a minus K over M. And a minus B over M. We need to invert that. And what was B? 0 gamma over N. We now need to invert this matrix symbolically. And if you have a calculator, TI-89 with computer algebra, it'll do it for you. Just have to know how to do it, how to put it in. MATLAB can do it also if you use the symbolic notation. Let's just do it manually. What we're going to do now is we're going to take S times the identity. There's SI. And now I'm going to just go ahead and move that minus sign into the A matrix. And I now have 0 minus 1. I have K over M, and I have B over M. And I want to invert that. I'm just going to do this on the side. As an aside, I want to compute that 2 by 2 matrix inversion symbolically. Or let me combine those two matrices. The 1, 1 entry is simply S. The 1, 2 entry is simply minus 1. The 2, 1 entry, K over M. The 2, 2 entry is S plus B over M. And do you remember how to invert a matrix? Didn't hear. So this is now 1 over the determinant times the adjoint matrix, right? And the adjoint matrix is the cofactor matrix transposed. Okay, end of story. Let's go on. Let's do that. Meaning, what's the determinant of this? That is now the diagonal for a 2 by 2. This is pretty easy. We simply have the product of the diagonal minus the product of the off diagonals, and that's our determinant. Doing that here, we have S times S plus B over M minus a minus K over M. And I'm going to probably refer to this as delta the determinant. And that's just a polynomial in S. It should be a quadratic. It should be second order because we had a second order system. And you can see that we will obtain an S squared. Yes, we're feeling comfortable a little bit better. And that's just going to be S squared plus B over MS plus K over M. And that should look very familiar. That's the denominator that we really were wanting. Now what we want to do is we want to put into here, we need to multiply it by the adjoint matrix. And what is that? Well, that now is going to be created by taking the cofactor matrix and transposing that. Do I want to do that in, let me do it in 2 steps. So I'm going to take the cofactor matrix and transpose it later. What's the cofactor matrix? Well, to find the cofactor for the 1, 1 entry, I simply remove the 1 row, I remove the 1 column, and I take the determinant of what's left. And in this case, what's left is a scalar, and a scalar is pretty easy to find the determinant. And that's my cofactor for the 1, 1 entry. That's going to simply be S plus B over M. Is that clear? Now I want to find the cofactor of the 1, 2 entry. If I do the same strategy, I remove the first row and the second column, and I'm left with K over M. Take the determinant of what's left, which is K over M. But I need the cofactor, so I need to scale it by minus 1 raised to the 1 plus 2 power. First row, second column. Is that making any sense? So I now have minus 1 to the 1 plus 2 times what was left when I removed the first row and the second column, which was K over M. What's the 2, 1 cofactor? I remove the second row, first column, and I have minus 1 left, and I take the determinant of that. But I need to scale that by minus 1 to the 2 plus 1. And those are odd. I'm really scaling this guy by 1 plus 1, minus 1 to the 1 plus 1. And that's going to give me just 1. Wow, are we out of time? So if we hurry up, what's the 2, 2? That's just S, isn't it? Scaled by -1 to the 2 plus 2 if we really wanted to. And now if we transpose that, we end up with 1 over delta. The diagonal stays the same in the transpose. We have S plus B over M. Down in the 2, or in the 2, 1, we have -1 times -1. That gives us a 1 when we transpose it in the 1, 2 entry. Upstairs we have minus k over m that comes down there, and down here we have s. If you now use that in your expression for g of s, just give me 30 more seconds, we had c times si minus a inverse, and that's just what we found, s plus b over m, 1 minus k over m s. Whoops, that was supposed to be 1 over delta. That's just a scalar that we're dividing by, and then times b, which is 0 gamma over n. So this we could pull out here if we wanted to, if that made you feel a little bit warmer. If you do that multiplication, you should end up with where delta is our s squared plus b over ms plus k over m. And we were going to do Bode plots and all sorts of things. I went too slow, but I hope now you can see how to find the transfer function from a state space representation. If we go ahead and perform the multiplication, this is after class. I'm just wanting to complete this thought. G of s now, the c times that numerator of our si minus a inverse matrix, the 1, 0 will really just pull off the top row in that matrix. So we have s plus b over m for the first column in that first row, and then 1. And now we have our input matrix, 0 gamma over m, and that's then multiplied by this 1 over the determinant. And these 2 by 1 times a 1 by 2 times a 2 by 1 matrix will give us a scalar. We have s plus b over m times 0 plus 1 times gamma over m, and we then end up with gamma over m in the numerator, all divided by the determinant, which the determinant was s squared plus b over ms plus k over m, and that produces then from our state space representation the same transfer function that we had in the other two cases where we were starting initially with the differential equation, and the second case we were working with the transfer function, with the block diagram, and here we have generated or completed our discussion of finding transfer functions by going from a state space representation, which was the c times si minus a times b, and the d was 0. That gave rise then for our particular mass spring damper of the same transfer function g of s that we had obtained from the two earlier approaches.